Thank you. I'm happy to be here with you. I'm going to talk today about a work called call-guarded abstract definitional interpreters. Is this too loud? And to set the stage, I kind of want to talk about a methodology called abstracting abstract machines, which you may be familiar with. But what abstracting abstract machines, or AAM, gives you is the ability to turn a small step formalism, or a formalism of your small step semantics, systematically into a static analysis. And the way you do this is by taking the state space of your formalism and redirecting all recursive structure through a central component called the store. The store is going to come up several times in this talk. And then finitizing the address space of that store. And that, in effect, finitizes the execution space. Now, two important properties of a static analysis are soundness and computability. And the AAM framework offers computability very cheaply because with a finite state space, you can just turn the crank on your analysis and you're guaranteed that it will terminate. So there's a spiritual sequel, kind of, to abstracting abstract machines, which is abstracting definitional interpreters. And this follows the recipe fairly closely. It's a little more accessible because you express your semantics as a definitional interpreter written in monadic style. But you do the same kind of indirecting of recursive structure, except you do not indirect the stack through the store. And the result is that you get a static analysis which is sound and computable and has high control precision. So I just want to make a little bit of an analogy here, that if we imagine that our concrete semantics is rich in behavior and it's very detailed, and that the static analysis is a necessary approximation in order to be computable. And so it gives us a decent picture of what's going on, but certainly some of the details have been discarded or lost. And I want to illustrate how that can happen with some examples. So this is just a simple example where we have an apply function, where you hand it the function and its argument, it applies them. And it's called twice. And in this program, add 1 will only ever be applied to 12, and sub 1 will only ever be applied to 10. But the analysis that we're considering now is a context-insensitive analysis. And what that means is that every binding to the variable f1 and the variable x1 are going to be mapped in the same place in the store. And that means that there will be 2 values for each. So when the analyzer considers this function call, in order to be sound, it's got to consider every value mapped for those variables. And so the analyzer will associate add 1 with 10 and sub 1 with 12, associations that would never occur in the real program. Now, we can solve this problem by adding context sensitivity. And the way we do this is we pick a notion of context. A very popular one is from KCFA, which is to keep track of the last K call sites encountered in execution. And those serve as your context. And that context qualifies every allocation you make in the store. So you can see here that this store now has 4 mappings. We've got the same variables being mapped, but each one is qualified by the call which affected that allocation in the store. And so you can kind of glean from the store the correspondence between the arguments to apply. Now, when the analyzer encounters this call, the same call, it's going to encounter it in 2 different contexts. And because it has the context in hand, it will look up precisely the variable it needs to, or precisely the value that is. And we will no longer have this spurious correspondence between add 1 and 12 and 10. So what context sensitivity gives us is a little bit of a clearer picture of what's going on with our program. But there are two problems with it. The first problem is that the abstracting abstract machines framework applies the finitization uniformly across the program. And when we add context sensitivity, we get the same finitization, but at a finer grain. And the result is that in parts of the picture with detail, we do get a better understanding of the program's behavior. But in parts of the picture that are more uniform, just to really stretch this analogy in the background, we are still paying for every pixel with analysis effort, but we're not getting much more information about what the program is doing. So it's not a useful, or it's not a cost-effective use of our analysis resources. The second problem is that increasing the context sensitivity only happened to work for that program. So if we refactor the program, what I've done here is just eta expanded apply 1 to apply 2. Now we're in the same position we were before without context sensitivity. That is, we make a call to apply 1, and the analyzer correctly keeps track of the context and is able to distinguish between the bindings. But then every call made to apply 2 is made in the context of apply 1, and the analyzer has no means to keep these bindings distinct. And actually, it's worse than the context-insensitive example because we're paying for context sensitivity but not getting it. So to finalize the analogy here, what I have on the right is it's a portion of the Mona Lisa that was constructed using 50 translucent polygons, and it was constructed using a genetic algorithm. And the analogy I want to make is that part of my work is to develop analyzers that are more responsive to program structure so that we get better answers for a given amount of effort. And in some sense, it's unavoidable that our analyzer would be sensitive to program structure. It's a theorem that any static analyzer is going to be sensitive to some intentional properties of the program. But the goal is to be more responsive to the program. And this work is a step in that direction. So now I want to tell you what a call-guarded abstract definitional interpreter is. So it's a hybrid interpreter that contains a full copy of the concrete and abstract semantics. The concrete semantics are completely precise. There's no finitization involved in them. And the abstract semantics are pulled just from an off-the-shelf analysis like KCFA. And the way the interpreter works is that every evaluation is optimistically started using the concrete semantics. And only when the analyzer determines that that analysis will not converge with those semantics does it degenerate to abstract semantics. And so on any given evaluation path, it will continue to evaluate in either concrete or abstract. But when it encounters non-tail evaluation, so for instance, if it encounters like a function call and it's evaluating the arguments, it will revert to concrete semantics on the off chance it'll get better precision. So just a little bit more formally, we've got this state space, and the important thing to see here is that our stores are addresses to values, and the values are either abstract or concrete, so they coexist in the analysis. And we've got this judgment here, this evaluation judgment. The first 4 terms are familiar from maybe a CESK or a CES machine with a timestamp. The M component is an evaluation mode. So every evaluation of a configuration is done in a particular mode, which is either concrete or abstract. And then the C corresponds to a call cache, which is defined by the call guard, which is a parameter of the analysis. And we offer this theorem that if the call guard satisfies certain properties, which I'll go over momentarily, then the analysis is computable. So the call guard monitors every function call and gets to determine under which regime the function call is evaluated, concrete or abstract. And the condition that it must satisfy is that it must supply an ordering on its call cache with no infinite ascending chains, and it must increase monotonically on any given evaluation path. So the paper describes two example call guards, a reentrancy guard and a size change guard. I want to go over those briefly. So the reentrancy guard uses a call cache that is just a set of function entry points that have been encountered on that evaluation path. And what this allows you to do is maintain concrete interpretation in any tree in the call graph. So if there's no recursion, if there are no cycles in the call graph or in the subgraph that you're in, then you maintain concrete interpretation. So for example, we could eta expand arbitrarily in our previous example and still maintain concrete interpretation. I just want to show a little bit of an example of this in action. So we've got a simple example or a simple program here that will just loop. And what I have on the left here is the abstract interpretation of this program. And as you can see, it converges pretty quickly. On the right, we have the call-guarded interpretation of this program. And so what we've added to each configuration is the mode, as you can see, and the set of entry points. And I just want to point out, if you look at the environments of the abstract interpretation, you'll see that we have variables mapping to variables. In this, we have variables mapping to indeterminate addresses, but these are concrete addresses. And so the analyzer begins by allocating concretely in the store, and then only determines once loop has been entered a second time that it needs to degenerate to abstract, and then finishes the analysis. Okay, so that behaved as we would expect, because we would not want to just kind of go on forever analyzing loop. However, here's an example, factorial, where using a reentrancy call guard is very unsatisfying, because it's fairly apparent that this evaluation is going to converge. And so let's shift and talk about the size change call guard. So the size change call guard is based off of this principle called the size change principle for program termination, and it's this. A program terminates on all inputs if every infinite call sequence would cause infinite descent on values under a well-founded order. And this is from Lee and his co-authors, and the idea here is that if you can characterize the argument descent from a function to the function it calls, the parameters, that is, and then you can compose those characterizations to get an account of argument descent across function calls, then you can use this principle to determine whether the program is guaranteed to terminate or not. And the way that they characterize argument descent is with something called a size change graph. So this program at the top has two mutually recursive functions. And what we have underneath are some size change graphs for them. So on the far left, we've got a size change graph from F to G. So the call in F to G passes its parameter directly, and then one less than one of its parameters. And that's reflected in the size change graph, where we have X has an arrow to A, and it does not descend, but it does not ascend. And then Y has an arrow to B, and this less than means that B is strictly less than Y. So that's a size change graph. There's an alternative notation beneath. And this is how they characterize argument descent from call to call. And you can compose size change graphs, that's on the right, just by following paths with edges, and you get the sort of least strict annotation on the resulting edge as was on those edges, or the most strict, I should say. Now, how do we apply this? So there's some great work by Phil Nguyen where they apply size change monitoring to offer termination as a contract on functions. And basically what that means is dynamically at runtime, they watch function calls, and when a function calls itself, or sorry, when a function is entered and has been called before on that path, they dynamically compute a size change graph of the actual arguments from the previous call and the current call, and they apply this size change condition. So there's this condition that you can property of size change graphs that tells you whether or not there are any infinite ascending or descending sequences. So this is fairly straightforward to cast as a call guard in our framework. And so that's what we do. We have a call guard where we detect when a path violates the size change condition. And the call cache is a map from function entry point to a set of size change graphs. So I won't go through this example in excruciating detail, but on the right I will show that the first time that factorial is entered, the entry point of factorial is mapped to the unit size change graph, and then on every recursive call, we compose the current size change graph with whatever the difference is. And the effect is that this slide, even though it shows a hybrid analysis, is showing just concrete interpretation. So the size change call guard is able to maintain concrete interpretation on this program. So I want to talk a little bit about the ordering we use, the value ordering we use for size change. I'm going to go to the second slide first. So the language that we use is essentially ML. It's got functions, data, and structural mutation. And so the ordering we use on functions and data, let's talk about functions first. They're standard off-the-shelf orderings. So for functions, you have that if you've got a function over the same, a closure over the same lambda, but one of its arguments is, or one of its environment variables is smaller, then that counts as smaller. Anyway, the idea is that they are off-the-shelf orderings, but you can modify them if you want. Okay, I'll briefly talk about our empirical evaluation. So we use two sets of programs. We evaluate it on two sets of programs. One of them is a standard program corpus for analysis. These were programs crafted to demonstrate the effectiveness of certain analysis techniques and approaches. And the second one is a subset of Larceny R6RS benchmark. And so there's a lot of different behaviors that are exercised in these programs. The result, kind of the high order bit here, is that call-guarded abstract definitional interpreters, the hybrid analysis, was able to maintain concrete evaluation for most of evaluation. So just in interest of time, I'll show you this. So actually, I take it back. Okay. What we're looking at is the results when we look at, okay, so when the analyzer runs, it's in a mode that's either concrete or abstract. And the analyzer in concrete mode may end up getting an abstract result. So we measured how frequently, when run in a concrete mode, does the analyzer get a concrete result versus an abstract result. And we compared that to the corresponding abstract interpretation that is always going to get abstract results. And we kind of compared the number of concrete results we got, and the upshot is that for most of these programs, we were able to keep the interpretation completely concrete. That sort of makes sense for benchmark programs because you would expect those to be deterministic and they specify a single run. It's a little surprising for the programs crafted to exercise static analyzers because it means that using a size change call guard, you are able to just easily handle all of the patterns that, that techniques were developed to handle individually. I will skip this. So there's still work to do, obviously. The Ackermann function satisfies the size change termination condition. And so in our framework, it is technically computable, but not effectively computable, or effectively, I guess is the wrong word to use there. Anyway, so we're looking into ways to proactively abstract interpretation to accelerate convergence. And we also want to evaluate on larger programs and kind of see how it behaves under those conditions. Thank you.
Hi, Benjamin Quiring from UMD, Maryland. So this first bullet point is something that I was thinking about. Like, you might spend a ton of time evaluating factorial applied to 42, then to later on add it in your abstraction to top or something and basically destroy your result.
Right.
So it seems like something that you could do is look into the future, maybe using lazy evaluation to delay actually evaluating factorial of 42 until you actually figure out that you need it to be a concrete value to actually do something later on in the analysis. Have you thought about doing something like that?
I have not thought about that specific technique. That's an interesting idea.
Let's talk more after then.
Yeah.
Hi, I'm Jay Lee from Seoul National University. I really enjoyed your work. I enjoyed reading the paper as well. I have a small question about the size change detection. So does it work for arbitrary like integers, or do you assume that the domain is just natural numbers?
It works for integers, but our measure is then on the magnitude of the number.
Oh.
You have to ensure that it is a well ordering.
Okay, so even if it's like negative numbers, it should be increasing towards 0.
Yeah, I mean, if you admit integers, then you use something like the magnitude, yeah.
Okay, thank you.
Yeah.
Hi, I might have missed it, but what happens if the main function takes an external parameter?
Oh, I didn't talk about that. The paper does, but in many instances, you're able to still maintain concrete control, even though abstract values are flowing through. Once control depends on an abstract value, you degenerate to abstract.
Okay, so you can be in a. This sounds a little bit like you're in a mixed mode, right? Where part of the values are abstract, but then not all of them, and you keep on going concretely as long as you don't read from them.
Yeah. So if you think of like the map2 function, that it's map, but it takes two lists. One of the lists is abstract, the other is concrete. It'll follow the concrete one and give you perfect precision following that, even though there's an abstract value that it's sort of looking at too.
Okay. Cool. Thanks.
Okay, so this might be a little bit of an ignorant question. How does this compare to concolic execution?
So concolic execution, good question. As far as I understand, concolic execution is not intended to be sound. It's a way to just combine dynamic analysis with symbolic execution. And sort of a design choice from the very beginning of this was to achieve soundness and computability, but there are probably deeper connections to look at there.
So maybe there's time for one last question while the next speaker starts to set up. Last question?
So you did this for the abstracting definitional interpreters framework, but have you thought about trying to reapply that back to the small step world?
Not seriously.
Okay.